Thank you, Professor, for inviting me to your seminar. So thank you for your kind introduction. So let's get started with this this diagram. So in the era of AI, I'm also using the AI quite a lot. So I gave the abstract and some of my ideas about this seminar, and then they drew this diagram for me. So as you can see, you are the experts in the designing mobility and all this connection and these systems, and then there are all these malfeasant attackers who's trying to interfere with this critical, safety critical infrastructure. So what you're doing is safety critical infrastructure, and analytics on this is very important. But in every connection point in here and the system itself are the targets of the malfeasant. So I'll try to give you a little bit of some existing technology overview, and also I'll try to give you some insights that you may need to apply when you design the transportation related or this mobility, especially hyper-connected mobility system in your research. So first, a little bit challenge in designing safety critical mobility system. I'm just going over some of the technical challenges in relation to security. So modern advanced mobility system, what you guys are designing are mostly controlled by computers, and they rely on privileged software. Most of them rely on OS kernel to be secure, but any vulnerability or compromised OS kernel can lead to total loss of control. And this mobility system, especially in the era of AI, is now controlled not by human, but by AI agent, and with least or no intervention from human users, right? So this becomes a more serious problem. And especially for example, a fully automated self-driving vehicles and totally unmanned area vehicles, and the autonomous control and driving is very, very critical. And any sort of the engagement will be done by AI agent. And then in this case, the security of agent and connectivity between agent and the system and the reporting infrastructure and some of the sensor information that the control decision is based on is very critical information. So ensuring the integrity of all this system is quite challenging. And also the control authority itself is shifting from a human to the AI itself. And as the cyber and physical systems more tightly integrated, and the risk for the security issues has been escalated, and especially the other systems can be a little bit tolerant to the latency. But a lot of the mobility critical systems, safety critical systems, are latency sensitive, so they cannot accommodate 1 or 2 minute delay. But sometimes the AI control loops, have you used the LLM? Do you feel that it's very fast, like a bright lightning fast? No. Sometimes that's very slow, and then sometimes even slower. And I think the AI control loops oftentimes does not meet strict real-time guarantee that's required by a lot of the hyperconnected critical mobility systems. So the criticality of latency in the mobile system, it comes to especially those denial of service availability attack too. A very short, brief denial of service attack could crash the mobility system, and it also involves human death or some physical crash. And also, in terms of the privacy issues and critical information and sensitive information issues, some GPS coordinates and destination information, and those can also expose the some of the confidentiality or privacy guarantee that a human deserves to have. And that's the sort of confidentiality issue. And then I'll explain this hardware isolation issue in this challenge. So traditionally, software-based security systems are deployed to make sure that the system that we're running, and if it is a safety critical system, then we're supposed to monitor very carefully to see if they are working in the manner that we are expecting, right? Otherwise, we can stop the system, we can reboot the system, things like that. And then to do so, we do this monitoring. And this monitoring mechanism is run especially on your same system as another software. So because they share the same environment hardware and they share the same software environment, the traditional method of doing so requires the expanded traditional the sharing the same software the execution environment. The software monitor itself basically share the same vulnerabilities with the OS kernel. If the OS kernel is compromised, then the software runs on top of that the OS. Even if it is our safety critical monitor, and that software monitor itself is under the control of attacker, so there is no way that we can have the assurance. So this requires the critical monitor should be this sort of the critical monitor should be separated from the rest of the software system. So that was the requirement, the need for the physical separation. So one of the mechanism that I'm going to share with you today is this like a hardware-based, physically separated monitoring system. And then another one that I'm going to share first is the connectivity problem between all these critical components, and then the controller and agent controller. They control the remote autonomous vehicles and ships and mobile systems, and the connection between them. Any sort of the interference between in this connection it's a critical issue. So, have you heard of have you watched the movie the Interstellar? Do you remember that they hijacked one of the UAV, right? So I think that's very feasible. So you can hijack control of some of the remotely RPAS-like system, remotely piloted autonomous system, things like that. So this is the second part that I'm going to talk about is more like here we want to make sure the safety critical system is running without any sort of the malicious behavior or normally. And we need to keep monitoring their execution behavior and on the side. But if we run this monitor as another software right here, then if operating system is under the control of attacker, then that sort of monitor itself has no use. So then we need to separate this sort of monitor outside of the target software execution environment. So that's sort of the idea of Interstellar, so basically hardware security module, the monitor that we developed, we researched on. And I'll show this one as a second part. And then lastly, I'm going to discuss the one slide, briefly discuss about the AI agent. What does AI agent means and what are the security issues and what does it mean to a lot of transportation design that you guys are working on. So, all right, with that, let's start with the first one. So hello dialect. So this is the every communication that you know of, right? HTTP, and it ends with S, right? Do you know what does S stand for? That's SSL, Secure Socket Layer. So most of our communication right now, what we're doing is based on Secure Socket SSL layer, SSL, or TLS. It's 95% of, I think, word network communication is done over that TLS and SSL. Why do we use that? It's an encrypted channel. And so do you remember that the Google and some of your search engine in the past, you didn't have this S at the end. You use HTTP, but at some point in time, you know that, have you noticed that it starts with S? Do you know why they add an S to it? If you didn't do it, then all sorts of the service provider, someone who provides the routing service and DNS service, the network provider, they see all the search keyword that you are typing in. Do you know how they make money on that? They can make money because if they know that if they see the spike on certain the vendor's name very quickly, they know that it becomes very popular and they can make some money by investing in something. Or there are a lot of privacy leakage related serious consequences. So they added secure socket layer as a base. That's why we see the HTTPS. So what I'm saying is that when you design like a remote controlled the outpass system, their communication between them, you have to use some special radio signal, etc. But at the end, you need to encrypt that channel, right? That channel usually uses a TLS, SSL, or IKE, the IPsec. So one of those. Now, that's not the end of the story. Because of the way they designed this HTTP, the SSL and TLS, you need to interfere, you need to engage with the target as you're the authorized user, and you're trying to control this system, then you need to make yourself authenticate them by sending all this like a server certificate, whatnot, and then you send the client certificate and your username and password at the end, right? So these are a little bit lengthier process than just sending a single client hello packet at the beginning. And why this? And then every attacker, every authenticated user, whether you are the attacker or not, the server has to wait until the client sends the certificate. So one of the problem of this approach is that the server must accept connections to the unknown attacker until they send their certificate. This is very akin to opening your house door first to verify any random visitors and their ID, and then check it, and if they don't meet your requirement, then you have to close it. What if they refuse to go out? So that's open the case of vulnerability. Have we seen the vulnerability in the TLS and SSL in the past? Do you remember? Have you heard of Heartbleed attack and Proton VPN hack? There are two times. It's a very serious problems. And that's the sort of TLS. So we started the idea of changing the assumption of this method of authentication. Every authentication, by definition, you have to make a connection first, and then you let them send you a certificate or some password, and then verify it. But that's not safe, is what we started when we started this Hello Dialect project. The name Hello Dialect comes from the fact that when we send the client hello, we're not sending the same hello packet. We send a slight variation of hello by adding some signature in the header field of hello packets. And because that's the random ID field, and it does not violate any standard of TLS and SSL protocol. So when we add a hello dialect with authenticated information, if it is authenticated packet, then it will be accepted like this. It will be accepted and then go through here. But if the attacker of course, attacker will not have the predefined certificate, and they cannot put the correct authentication information at the header field of this client hello, the very first TLS hello packet. So in that case, when they send it, then we verify the this filter will verify whether the hello packet contains the right header information or not. If not, they simply drop it. So what's the main change here? I don't have to open the door every time to verify the certificate. I basically give a chance only when the other end is pre-authenticated. So this has the very interesting issues. So we save ton of network bandwidth. So oftentimes the KAIST can have VPN server where 10,000 users can access at the same time. But more than 10,000 users, then we're under the denial of service attack. When I presented this idea to one of the game company, they love to try out this solution. Why? When the NC or they launched the beta new game, right? Then everyone joins online at the same time, and their capacity is 10,000 person at a time. But attacker usually demand the ransom money. If you don't pay me, then I'll have my botnets to make just a hello connection with you, because they don't have to send the real certificate. They don't have to be the paid user. All they need to do is just make these connections, and they can only make a support connection up to 10,000, and starting 10,001 or even 20,000 clients, then they won't be able to support the legitimate users. But if we can drop the non-legitimate users very early on in the very first packet, then only the the authenticated users can go through, and they're the one who can finish sending their certificate. So this is the main idea of the dialect hello. So it's more like this. When someone's knocking on my door, say hello, then I say, oh, that's stranger. Don't answer it, right? And then someone knock on the door. Hello, it's mom. Hello, it's dad. The kids in the house, they can easily tell whether the very first voice is the authenticated user or not, right? If so, then they now open the door and then check the ID and then let them come in. So that's the idea of TLS hello, and we are hoping that we can apply this to make the communication between the hyperconnected mobility system as secure as possible. And with this, hopefully the incident and VPN hacking incident and Pulse Secure and our KAIST also got hacked on this Pulse Secure case, right? And we had serious issues on this one too. And the hello dialect can effectively prevent all this sort of the exploitation had this happen again in the future, right? So that's the sort of the communication issue. So before I jump into the next topic of the designing the secure secure hardware-based monitor, any questions? Oh, yes.
I think you want to check your verification at the first time.
Right.
So, as I know, the DDoS attack is very similar, like making a huge traffic to the server.
Right.
By attacking this concept, as I know.
Yeah.
And then your method can prevent like kind of DDoS attack also.
Yes, exactly. So the excellent question. There are two types of DDoS attack. One DDoS is just the pure scale. It doesn't matter. Then they need to send really huge traffic. Then it will clog not the target application, but the intermediate router will be clogged first. But when they try to do that, that can be very, very noisy in the network infrastructure. They will be detected immediately. But most of this, like a ransom-based demand, the denial of service attack, is not in that category. The other category is the application DOS. This application server can only serve up to 10,000 users. That's the limit. More than 10,000, it's not a DOS. It's like we're too popular and so many users are trying to use it. That's it. So then, in that case, you have to increase your capacity, right? But my point is that in that case, if the authenticated user is under 5,000, right? Then this client hello will be handled 5,000 users all the time. Even the attackers are trying to make a connection. But for this method, they can only open when you close this, right? You have to have at least 1 or 2 minutes to time out. So when they send the client certificate, if it is a DOS, they're not sending it immediately. They're delaying it as much as possible and then send it, and that certificate is invalid certificate, right? Because they're not authorized users, right? So then they say that unauthorized users say, I need to close the connection, and that takes up time, and that's the application DOS. Right. Excellent question. Any other questions? All right, then let's move on to the other aspect. Now this is communication security. Now the other one is how we design this hardware-based, totally physically isolated security monitor to assure any sort of the attack on the system can be detected. So that's sort of the idea. And to give you a little bit of high-level the background. So here's the sort of the overall system architecture diagram. And then you run your application. Sometimes you run on top of a hypervisor, and you always install your guest kernel operating system. And this guest kernel operating system directly use your CPU and hardware, or sometimes going through the hypervisor, etc. And all hypervisor is written in software, and kernel is written in software, and application, of course, written in software. A lot of your mobility application. Here, the monitor can be located right here at the kernel. So when you install some of the virus scanner, and you install in the kernel. But if kernel is under the control of attacker, and it's of no use. Sometimes you run on the virtual machine, VM machine, and you run your software monitor inside the hypervisor. But if hypervisor is under the control of attacker, you have no use. And then some encrypted computation is so-called the TE and SGX. That's another like confidentially the method for the hardware-based Intel SGX ARM Trustion. But their computation is totally encrypted, and therefore some of the monitoring is infeasible. So in that case, if they're the one, you're the one running the malicious software, but that's totally encrypted and cannot be seen by your kernel, the monitor, and hypervisor monitor, because it's encrypted, that's the huge problem. So to address all this challenge, we designed the hardware-based monitor that runs on next to the CPU. So that's what we designed. And this main idea is that here's the application that runs, and every instruction of the application, binary code, it's being fetched and fed into the CPU and run it, etc. But at the time that it is being fetched to the CPU, and we monitor the instruction flow. So this is often called instruction tracing security monitor. And some of the previous approaches that instructions fetching mechanism, here's the overall diagram of how does the instruction is executed in modern pipeline hardware architecture. So the reason that we use instruction fetch, instruction decode, and execution, and memory access, and then final the commit, is that every instruction requires about these 5 different stages, and for each different stage, when you process the first instruction, while they're being in the instruction decoding stage, and you're fetching the next one. So that's basically every instruction is being fetched in this modern pipelined CPU architecture. And then our trace unit is basically monitoring and these behavior and see whether their instruction flow is correct or not. Now, so let me show you the example a little bit, then it will be a little bit clearer. So I think here let me show you this part first. So first, instruction A is being fetched, meaning that the CPU is executing instruction A. Let's say that instruction is the MOV, move value A to memory location the X. Then that's the instruction A. And we just copy the instruction passively to our monitor. And our monitor will record whether that particular instruction is safe or not by keeping all this movement into final state machine and one by one. So instruction A is the being monitored instruction. And then when instruction A is being inspected and second instruction B is fetched. But instruction B is the benign instruction that we're not keeping an eye on. So for some critical instruction, CL3 and some critical register value change instruction, those are changing the mode bit from user to kernel and kernel to user, and that's very critical. So in that case, those are the instructions that we need to keep an eye on. So you're supposed to, at the user level, and you will not be able to execute the kernel level on privileged instruction, but suddenly I see some instruction, the monitored instruction like this. Instruction A is like a privileged instruction that we're monitoring, and then in this case it's coming in. Then we immediately know something went wrong with the system. So instruction B in this case is the benign instruction that we keep moving, but now instruction A is in the stage of the getting into the decoding and then the memory stage. And then when the instruction A and B are in the pipeline, now we're fetching the instruction C. The instruction C is also not being monitored. It's a non-critical instruction that we don't care too much about. For example, this all depends on our state machine and which memory operation, which instruction that we're trying to monitor. It all depends on the algorithm of detection algorithm. So instruction C is not recorded, and then the next one is instruction E. And instruction E, when instruction E is fetched, all the previous instructions here, like instruction A is about to finish, and then B is here, and C is here, D is here, and then A and E is the one that it's a very critical instruction that we are monitoring. When instruction E is fetched, then we record, this is the important instruction that we keep an eye on this, and then we record these instructions behavior into the hardware designed state machine. This state machine record whether their instruction the target location is okay, or are they trying to jump into some unknown location, outer boundary of their memory, allowed memory space, things like that. So those are all the detection logic that we developed, and we record based on this fetched instruction. We record all these states, and if the evaluation of this internal state machine determines, oh, this is an attack, then we the state machine will pull out saying that based on the instruction A, and then now we see the instruction E again, and based on these two, we'll see that this is the attack, and we need to take an action. So this is the more like when you're running the autonomous driver, the very safety critical like mobility system, or not just moving mobility, but also some monitoring some transportation mechanism, and some of the systems are under the control of attackers, it will show this sort of behavior, and it will be detected by this hardware. Then what are the counter the measure actions, like restore the recovery action, is depending on the attack detail. If the attack is trying to update very critical, safety critical memory value, so in that case, we simply block that instruction to be committed. They are being like decoded and executed, and then the memory access, and then finalize it. Before they finalize it, if we decided to unroll some of this, maybe you remember Architecture 101 when you learn in the undergrad class, you unroll that instruction. Basically, that instruction has not been executed. Same effect. So that's the perfect way of defending against any sort of the malicious attempt, right, to compromise the system. So that's what we developed. So overall, one of the use case is that, have you heard of return-oriented programming? This is the most advanced sort of the attacker's technique. The idea is usually the easy solution is this. I mean, here you have malicious code dump, right? And when you're able to do buffer overflow, then you can just upload your malicious code onto some of the memory. But that sort of attack is very basic, and nobody is doing this for some advanced target. And because a lot of the critical core, the kernel core memory image, it is read-only. You cannot update it. So attacker cannot override some of the code portion. So then attacker comes up with a better strategy. The smart strategy is, instead of the writing your own attack code, you reuse existing kernel code as your code base, but instead of calling to the start of the function, you call in the middle of the function until you see the return. When you see the return and you're able to compromise the execution stack, you'll go jump into the next location. So it's like a return, lots of return, but you can jump into the instruction that you're trying to access. So it's more like gadgets of small code bits that you connected here and there, right? So that's sort of gadget-based, small gadget-based, the return-oriented programming. We call that return-oriented programming attack. And that's the modern attack. So if that sort of the attack is being deployed to one of the safety critical system in your mobility infrastructure, then what sort of behavior will be seen? The obvious one is the return will be seen a lot, right? And then when you do the jump to the next function, it's supposed to jump into the first location of the function. But return-oriented programming, they never jump to the first location of function. They always jump in the middle of the function, some random location here and there. And that's another no-no behavior, right? Malicious behavior. And we'll be able to detect that immediately, very fast. So that's sort of the overall architecture. Of course, we implemented all this in real hardware. And then another one is, have you heard of the row hammer, right? I mean, maybe you heard the row hammer, but I'm talking about cache timing side channel leakage attack is very difficult to detect in general. The idea is cache is the shared mechanism in the CPU, and you have one critical application that runs first, and then you are the attacker, the process. Then attacker process runs next to that after that critical the process. In that case, they share the same CPU, but the cache is remained without being flushed. So in that case, the attacker can infer what sort of value that the previous process, the victim process, has accessed. So that's open code. That's we call it the cache side channel leakage attack. And for that to detect this sort of the timing, the way they figure out whether the previous process, the target process, has accessed a particular value or not is based on the cache timing. Let's say that the target process accessed value named secret. Then the secret, if you access the same value, you will get very faster response. Why? Because it's been cached. But if the previous, the attacker did not use that secret value, then let's say secret is a 172. So if you query 172, then you will get very fast response. Then you know, oh, the previous process must have used 172, right? But when you try to do the 172 and you see the response is very slow, that means, oh, 172 has never been cached. So that's sort of the cache timing channel attack. It's more like the inference of what's left by previous user. It's a very simple idea, right? To do this sort of attacker, if the attacker is trying to leak some of the very critical password, right? 172, for example, then in that case, what's their behavior then? They're trying to measure the time very, very frequently. Timing measurement in your application, how often do you use it? Not a lot. Not a lot. And if you have to time out some operations for the sake of for the sake to assure the process should be continued, and then time out, and you have to resend the packet, things like that. But that timeout usually requires 1 or 2 minutes. But this sort of cache timing, you have to run it every millisecond level, even lower than the millisecond level, to detect the timing value. So when we see the instructions trying to measure the time very frequently, we can easily say, aha, they're trying to do cache timing. This is very dangerous then. Someone's trying to do cache timing attack. This means that malicious attackers are under the control of the process. At least they're running some attacking process within the system. Then you can do some counteraction against it. So that's another example. As you can see, this sort of the hardware-based mechanism, when you see the normal application, we see no performance degradation at all. But if you run the monitoring that interfere with every instruction, or they try to monitor all the memory access to assure the safetiness of the target, safety critical applications behavior is normal or not, then their software, the overhead will be 20 or 30 or even like a 50% or more, sometimes 100%. You get twice slowed down, right? But because it's hardware, it's very fast, and a lot of the memory bench and spec bench and LM bench shows that no overhead, sometimes even faster. And some of the lucky case, even like a branch prediction case, our next version of the outer Stella, and it actually shows a little performance improvement. Because because we squash some of the mispredicted value very well, and we allow only the branch prediction that the start of the function will be allowed. And that sort of filtering, sometimes even speed up the overall performance. So which was a little bit surprising result. So this is sort of the overhead. When we think about this, the monitor, software monitor, yeah, you're running software. You don't take up any new hardware at all, which is great, but it's slower. Right? And then also the critical one is the software monitor. You share the destiny of the operating system kernel. If the OS kernel is compromised and you run inside OS, then you are also compromised too. But despite this, the hardware-based, the monitor takes up hardware space. And this is the main concern in general. And a lot of the CPU and their area cost is very critical. If you take up huge area, then they don't like it. And then take up huge area means that you waste a ton of the battery or electricity or the energy too. So energy consumption is another concern as well. So this power consumption, perspective, overhead, and then also area overhead. In terms of area overhead, detecting those like a cache timing attack, it takes a very small overhead. It's like under the 4%. And this is done in RISC-V architecture. And another killer question is this. Wow, this is great. Then can we see this on my computer? No, until Intel, AMD, or the ARM, they adopt this and implemented that on their own, you don't see it. But RISC-V is an open architecture, and we implemented at RISC-V. And RISC-V area is, in general, very small. And even small, this area overhead is percentage overhead. So if it is deployed in the real Intel, AMD, or ARM architecture, it will be under 1% because their area is huge and our area is this much. And for RISC-V, their area is this much and our area is this. That's why it's under 4%. I mean, that's another just a minor detail. But overall, this portion is well accepted because it's very small overhead and we can do some very good benefits of monitoring most advanced ROP and ROP attack and the cache timing channel attack. The very complex attack will be detected when we added these components, but they takes up a little more, but it involves a lot of memory manipulation. So we need to keep track of those memory. That's why it takes up this much of overhead. So combining all this and we take up this, but this alone will only take up this much. So for this portion only, and we're hoping to apply this for RISC-V based unmanned aerial vehicle that's in Korea in the next year, and with the help of the I think the Korea governments and their I think a new project. So anyway, that's the sort of the overall hardware cost area. So to make a quick conclusion over just Interstellar, you can take away saying that, well, I think a monitoring safety critical system is not an option. It's a must. You have to do it, but when you do it, doing it on the same environment and same software environment is not a good idea. And you have to have isolated the environment and run it. And one way of doing it without affecting the performance of the existing software is doing it at the hardware level. And the hardware level is the right thing to do, but this requires hardware vendors' support and change. And I think an open architecture like a RISC-V does have our solutions. And so that's sort of the conclusion of the Interstellar. And any questions on this? So Interstellar is, okay, very good. So let me move on to, yes, sir.
So how is the complexity of the security monitoring logic managed for complex OS or large applications? It seems like the number of message states and transitions become very large.
Thank you. Super excellent questions. So we're not claiming that we'll be able to detect all of the security attacks. we can only detect cache timing side channel and ROP monitors. We can detect subset of advanced attack, but that's better than nothing. Most complex attack in general cannot be all detected by the hardware. So to do so, we have to have this sort of the maintaining shadow stack, and to address a lot of complexity of the operating system, the movement, and then to make it very accurate, then we have to use more resource. But this is the good bang for the buck for now, because only using this, we can catch very, very the critical ROP attack and the cache timing attack. So ROP attack is very critical because most attackers, the reason they attack the system is they want to control the way they want, right? So to do so, then they have to install some, like their own code, right? So their own code installation is blocked because everything is read-only, and then if you modify some kernel and critical location, it can be detected immediately. Do you know another anecdote of some of the latest kernel-based BPF door attack, the SKT and all those sorts of things? Do you remember? The BPF door, why they use BPF door, it's one of the kernel's extension, but if they were able to modify the kernel itself and the OS image, the detection would happen right away because it is being supported by many other OS vendors in general. But BPF door is the extension. An extension is supposed to change, and they hide the attacking code inside the BPF door. But if there is no such thing like BPF door, then they have to use something like this ROP, return-oriented programming. So reusing the existing kernel code. Then ROP behavior is one of the invariants of the attack. So therefore, as long as we can assure that every function will jump to the start of the function, if they jump to the random location, then it's ROP, and we detect it, and then inspect the machine again for safety critical, because it's really safety critical system, then it itself will cover most of the attack. But as Professor asked, we won't be able to cover all the complexity of the OS-based, like dynamic, the manipulating dynamic location and manipulating the legitimate location of the kernel. So in that case, we won't be able to detect it. Yes.
I have two.
Okay.
I found this is very similar, or at least some methods behind it seems like something we use similar, but it's not easy to grasp.
Mm-hmm.
But thinking of like if I'm using this, how do I handle this false positive case? Because if this is
false positive,
then we have to start the safety critical system.
yes.
How do we handle this is one question. Second question is,
False positive.
if the legitimate, the key for the legitimate elements, because we are operating a lot of like vehicles, mobility systems.
Yes. Big.
If one of the key for the legitimate elements is compromised, then what do we do? Because it's we have to operate it, but this is like somehow identified as like malicious.
Right. Malicious. Then, so the first one, let's the false positive, and second one is the response the guaranteeing the availability of the system, right? So let's see the false positiveness. So the false positive case, would there be any false positive? I would say the very simple algorithm, I wouldn't say that we have high false positive, like a timing channel, because let's say that you're doing the legitimate research, right? So in that case, and you're running ton of the timing, timing measurement. So in that case, we mistakenly detect attack. So in that case, and you have to let us know, and you have to turn off this thing and then do the experiment because you're doing experiment. But in the normal situation, that's not the normal operation in general. So, and then the response also related to false positive. If the false positive gives you the serious consequences, then if our response is to block that system, not running it, then if it is a false positive, then it's a legitimate operation, then we block it, then suddenly the car should go and then stop, right? Because of this false positive, for example, then it's more dangerous. It's far more dangerous than the attack itself, maybe. So in that case, how we design the response is related to how we can tolerate the mispredicted false positive case. So that's the first one. And then for the response case, like a multiple entity, and then one is like a compromise, then how can we handle? But that's sort of the graceful the regrouping or the having a redundancy is in general helpful, and then also in some cases, instead of blocking the operation, we let this go through, but we know what happened. It's more like that's more safe because we let them go through, but when the car stopped in the evening or when the entire system is being inspected, in that case we can inspect more carefully. So it all depends more at the high level. So response is something that the response that we can control is either we can flush it or we can just let it go and record it. So we record it or let it go. Those are two control knobs that we have. But at the more like operator level, at the application level, you have more higher level of regrouping or just or just let it go and then periodic inspection time. At the periodic inspection time, you can reevaluate or reboot that system, things like that. Yeah. So with these two are very immediate, and then now everyone's worrying about AI nowadays, and including myself. These are what we discussed is just this is what we discussed, right? The hello dialect and then this interstellar, and both are like very the critical components in the overall design of this the hyperconnected mobility system. This is last slide, and this is what's happening in the world in the age of AI. And then I also see that this will be happening very soon in the daily transportation system that I'm using every day. I see that right now the subway system is run by human operator, right? And then the bus will be operated by AI agent very soon. And then the sort of the robot physical AI. A lot of this physical AI is really the daily mobility system is at this location, right? And then who's sending the control order and then parsing their response in daily? I'm expecting it will be done by AI agent, and then this AI agent will summarize the report to the human user, things like that. So that's sort of the idea of AI agent. And this AI agent, agent meaning that it's like a replacement human, and it's more like the agent will use the existing backend AI system to do some decision, and it will impact some real-world changes. So monitoring this AI agent application running on system is secure and normal is one challenge that we're trying to address. Number one, this AI brain is not open. It's a black box because they invested in billion dollar, trillion dollars, right? And nobody opens the weights and their LLM, the operations. So we cannot tell whether this particular decision has been produced after it goes through all this AI system, or it was just manipulated by the attacker at the front. We cannot detect it. But how can we detect whether the system produces the result in the normal execution path, after they go through normal execution path, when we don't see the contents? So in that case, if we're able to see the instruction, and we expect that if they go through it, then we see a lot of multi-add million times, and then million times. We can count that and see normally they go through 100 trillion multiplication, but today they only gone through maybe 1,000 multiplication, and then you get the result, then something's not right. But that's just the one, that's just the one example, and we don't know how we can monitor without violating the confidentiality of the AI brain, of their safety. That's one aspect. And another aspect is that the connection between AI to AI agent and AI agent and physical AI is no longer controlled by human. So when we do a lot of operation in general, we do operation, humans operating it. Now, in place of human, AI agent will be operating that remote machine and remote systems in general. And in that case, assuring some of this connection in the case of AI agents being communicated together is another challenge. And the way we do sort of communicating between AI agent is mostly based on making a copy, traditional network. But some cases, the communication between AI agent does not need to follow the current network protocol because it's machine to machine. So in that case, they may come up with different protocol, or there's a ways of sharing data much faster than what the network does right now. So that's another aspect that we can think of. And then this knowledge base, do you know that, have you heard of in the 20 years ago, a lot of paper-based system will be converted into database system. Now, even with the database, we have a human operator in front of database, and then they type in the information and they change the information. Now that the very human will be replaced by the AI. The AI will control the database and backend the knowledge base. And that interaction is also, it's totally changed. So for example, I think a lot of transportation system, you need to collect lots of sensor data here and there, right? And then you have the collected location, and then they make a decision based on a lot of the collected information from distributed sensors, and that sort of decision oftentimes require human intervention. They see all this data and then they make a decision, and it will be done by AI. Then what are the safety and security issues? And then how we sort of assure this knowledge base that this decision AI is based on is secure or not. That's sort of another challenge too. So, and we have some of some solutions. I mean, some of the research project that they making sure that this AI agent is safe and security critical, and instead of just a normal, just any open source AI agent, how we can assure that is one of the TSA agent idea that we're working on. And then there's some components of this AI. What are those components? What are those software components? And it's often called the software bill of material. And then sometimes this S can be replaced with the AI bomb. So with this AI is built from which data set and what are their basic, the sort of the safety mechanism that they employed, things like that, will be declared in the bill of material. And then we also provide that information. The studying that is another one. And here is a network DPF applying the routine AI agent case. So hardware monitoring aspect here and here and here, and all this angle is what the outer stellar the technology that we use. And just this one is just the interesting trusted privacy filter idea is that when you as a human is trying to interact with the AI agent, and you oftentimes upload your private information, and the TPF as the plugin, as a Chrome and Edge plugin, or you go through maybe KAIST gateway service to access outside the outside AI service. Most enterprise in general right now, nobody can use the GPT and the Gemini 5, things like that, directly from your enterprise because they worry about you uploaded your Excel sheet and your corporate data, right, onto the system. So in that case, we need to filter them, but we still allow them to use it, and then we can restore the original private value, things like that. So that's what we did for the TPF. So this is the sort of the overall AI. With that, I think I'll end with Q&A. Thank you. Yes.
For your great presentation, and you mentioned about the filtering, physical, like when based on physical filter mechanism next to the CPU, and you block some
Right. We block if the instruction flow is malicious.
But
Right.
I saw some news, like we install some vaccine into our computer, and the vaccine can be the channel of attack. I saw in the news.
Yes.
Like vaccine have to prevent some attack, but
Yes.
But I'm curious, your filter can be some attack point, can be
Yeah,
attack point. Is it?
Very, very good. Excellent point. Excellent point. And here's my take. Vaccine is complex, and then vaccine is software. Vaccine by definition requires like data signature all the time, and they got updated 0.1, 0.2 very frequently. And then sometime during that update, attacker infiltrated the vaccine company, and then they install malicious software instead of real software on top. So you install it. Now you're running with the root privilege with attacker's capability, right? Attacker's code, you run the attacker code with operating system admin privilege, right? So that's the case. Now, if hardware-based monitor is installed, we detect it immediately in that case because we know that the normal behavior of this vaccine software. So if the vaccine software suddenly do ton of the timing attack, ton of the jump into the in the middle of the function, things like that, then we can detect it right away. And the other part, our logic is implemented in a finite state machine, and logic is open, and everyone can inspect it. But the software, the vendor, like the software-based, this complex virus scanner, I don't think they can open their code because that's their proprietary. And then it's far more complex than our finite state machine detector. Because we have to implement it in the hardware, we cannot afford to have complex looping and anything. We have to make it very simple. Therefore, that's why we cannot address a lot of complex real OS, like a DCOM or dynamic, the region, some of the critical, the kernel's dynamic region is being manipulated, things like that, we won't be able to detect it. But because our final state machine is verifiable, it's a final state, and then therefore we can show that it's almost impossible to embed that I mean, the way you describe it, to conduct the malicious behavior. Another one is you have to, because it's a hardware, it cannot be changed dynamically. So it has to be verified over and over and then put it in. And that's a very good question, yes.
Any other questions? So I have just one last question. If we go back to the previous slide where you showed some of like your ideas and some...
This one? Or?
AI.
AI, okay.
So I was very curious.
Yeah.
This is like emerging. And we also try to implement AI approaches for mission autonomy. So we mission autonomy.
Mission autonomy, okay.
So we try to make the operation of the mobility systems completely autonomous.
Yes, yes.
And there we use AI. We try to use AI.
Yes.
And we want to verify the AI agents.
Yes.
And otherwise, we can't really guarantee safety or all these things matters, especially for the air mobility. This is very critical.
Yes. And
at the same time, we try to actually achieve this autonomy.
Yes.
So it's kind of like a dilemma we have.
Yeah.
And what I thought was, unless maybe for the time being, we force the form of the output of AI, like some sort of like logic.
Yes.
As you use state.
Final state machine.
Final
Yeah.
state machine. We can maybe force the format of the output of AI agent as some behaviors or the states or some logic.
Yes, yes.
And having this, although it's a black box, if I have the output, then we can implement some sort of temporal logic or like a form method to validate the behaviors.
Right, right.
And I was thinking, looking at this, it will be very difficult to identify malicious intention or malicious attack by checking the logic and finite state machine approaches. And you mentioned you have also some limitations of the hardware computation power and so on.
Right, right.
And then the only way we can now do this is like forcing the
Output, yeah.
How do you think of this?
I think a really excellent question, and I don't know the answer to all of that. But if we can make us, where are the points that we need to assure, we need to watch? First, as you mentioned, that the input and output. And input and output is sure thing. And then when we upload the input, we try to whether the input is valid and etc. Especially to safety critical system, where the outputs are within the allowed boundary, and you have to check all this like a validation stage, separate from the AI agent, right? So that's what you're doing. So those are input and output checking. But that's very relevant to the application or domain experts. So we let them figure out that domain and define the allowed range and evaluation of that aspect. What we're focusing on is the in-between, the real execution. We're trying to make sure that this agent is behaving normally or not based on lots of signature. So someone says that power consumption is normally this much, but if it doesn't go through that and then pull out the result, that may not be the one that you have to trust. But in some cases, it doesn't go always use all the layers. Sometimes they use a few layers and then come out. So in that case, their consumption may be normal. So we have to figure that out. So normal execution behavior. And then if we do it at the instruction level, then the instruction level that we have to keep track is not the CPU instruction that I gave you as an example. Most of these instructions are the GPU and the application accelerator, the specialized instruction. And that specialized instruction carries very little the behavioral differences. So it's just multiple computation and again, and then some weights. And all they do is multi and add multiple times, right? So we don't see very like a detectable or signature, even at the instruction level. It's very challenging. But however, at least we can tell whether it goes through the entire execution flow or it's kind of dropped in between, or it doesn't even go through it and then it's somehow got the output, then we should not accept it. And another current safety mechanism that we do is like n-versioning. Instead of using only one, or for the safetiness, we use the two same service for high availability in general, at least more than two. That's the availability issue. But for the correctness, we need to have a different AI, the vendor, or different AI implementation, and with different code base, or the training is different. And in our example of finding some sort of the bug using AI, for example, if we use only one AI service, they said this is the bug and location, but we ask the same question with the other 5 different ones, and they say no. So in that case, the majority sometimes win, but sometimes the majority it's not true, because this is the most advanced one. They're the correct one, and the rest of them, they're not there yet. So in that case, the majority doesn't help. But in general, if we have some valid implementation with the same level, then making the implementation added variety intentionally different way is another way of assuring the safety decision coming from them for safety critical system. Yeah.
Listening to your answers, seems like one of the issues was black boxness. The second issue is also about AI isn't another key characteristic, which is stochastic, I think.
Yes.
Because normal behavior with these things based on, I guess, to me, it sounds like deterministic.
Non-determinism is a huge issue. Yeah.
AI agent is sometimes answering this way, sometimes
Yeah,
this way.
right.
Therefore, maybe we might need to address these issues.
Right. So excellent point. The non-determinism is sometimes good for creating creating new things, like very slight variations in the design and drawing picture. But for our systems in general, we hate non-determinism, right? We cannot even reproduce the bug if non-determinism gets in the way. Meaning that same input, you get a different output, depending on their mood, right? Depending on the day. We don't know how and when. It's so totally random, right? So it's a very difficult thing to address. So I think how to deal with the non-determinism is it's more like a training. We humans in general. I think I heard from the folks who are trying to build the foundation model for the AI, and when they got stuck with the problem, they always go back and how humans behave in that situation. So that's their wisdom. So applying the same thing to the critical system, when we run the critical system, like running the airplane, we do not depend on only single pilot. We got 2 other pilots, right? And make sure that they'll sleep well, and then they're well nourished, and then they stay alive, and they stay alert, right? And then the 3 different, sort of the input, and they are very well trained for, given the same situation, they're all trained for exact same safe, mission critical, like the safety behavior or restoration behavior, for example. So that's sort of the additional training to fit the purpose of the safety critical system is extremely critical. The current system that we're dealing with as the pilot right now, they are extremely trained on YouTube video. They're extremely trained on the online, all textual material and news, etc. And they're not trained on respective professors and their interaction. No, they're trained on, for example, I would say lots of trash material. So, but still, they are more like an encyclopedia of the web. And I don't look up Google anymore. I can always ask same question to the Gemini, and they answer very accurately. Yeah. If it is on the web, they do. So same thing. So I think for safety critical system, we can bring in the foundational model, but that foundational model does not know all this hard training that how many hours that we need to put in to train the airplane pilot. Maybe 3 years, 2 to 3 more years. So that amount of time and training is also required to train these agents. So that's sort of the. I don't know whether that would solve the problem, but I think that's the one potential direction that we can take. Yeah.
Great.
Right.
Okay. Thank you very much for the great talk once again. Please, guys, again, thank you to our speaker for the great talk.
Right. Okay. Thank you.